Okay. I've got some algebra up here, but I'm really going to get into proving trig identities. The only problem is there's some basic algebra you have to know, and a lot of people who think they know all the algebra don't really know all the algebra. For instance, when you take a fraction and you divide it by a fraction, you flip this around like this so it becomes AD over BC. And we run into this a lot in identities. You'll have a fraction over a fraction, you'll make it into one fraction. This is actually, although it looks weird, especially when you have trig functions, it's just the same thing because it's really A over 1 over B over C, so it becomes AC over, let's see, A over 1 over B. All right. Okay, C goes on top, B goes on the bottom. Here, it's actually the same thing again, but this time it's C over 1. But again, people don't recognize it. So I make three little rules here. And this is C over 1, so this is going to be A over BC. And of course, we can take a fraction like this and split it into two fractions. In fact, with the same common denominator. In fact, this is one of our big strategies in proving trig equations. And that's what we'll notice. Over here we have the difference of squares. You know, a squared minus b squared is a minus b times a plus b, and vice versa. If you can go this way, you end up with that. If you have two fractions like this, you can do the cross multiplication method, or you can use the lowest common denominator. For almost every trig identity I've looked at here in our book and on various sheets and things, you only need the cross multiplication trick. So that's all I'm going to teach. I'm not going to teach you how to really add fractions. So you go b times d, and then you go a times d, keep the sign. You keep the sign here, which is also plus, and that's b times c. And that'll get you through trig identities. That simple trick. You'll be adding lots of fractions with trig functions on the bottom, and you can do it. And then you'll be taking powers of things. You know, you might be taking the secant to some power, which is 1 over cosine. You've got to realize that you distribute the n in this manner, this power, and it's assuming that all roots exist. This is true. Same here. If all roots exist, then ab to the n is a to the n, b to the n. You should take some time and write these all down. Just like the 8 fundamental identities in trig we're going to look at, these are sort of algebraic identities. You have to know that this is true. Now we're going to come over here and we're going to look at the 8 fundamental identities. In class, I usually prove these. I'm not going to prove them here because I just want you to know what you need to know. By definition, the cosecant is the reciprocal of the sine. So that comes out nice and neat like that. Cosecant equals 1 over sine. Secant is also the reciprocal of the cosine, so it looks like that. Cotan is the reciprocal of the tangent. And it's very simple to prove that tan x is sine x over cosine x, and cotan x is cosine x over sine x. And then we have the Pythagorean identity, sine squared but plus cosine squared equals 1. And from these we can derive this one, tan squared plus 1 equals secant squared, 1 plus cotan squared equals cosecant squared. Now I would advise you to stop the video, make sure you have all these written down, and don't forget that when you write sine squared, it means you have the sine of x quantity squared. Okay? Another thing is this, when I give you one identity, like the cosecant of x, oops, let me write that better. The cosecant of x equals 1 over sine x. I've really given you 3 identities. This one, I can bring the sign up and say that the sine x times the cosecant x equals 1. Or you could say that the sine x cosecant x, sine x cosecant x minus 1 equals 0. Or even that the sine of x equals 1 over cosine of x, sine x equals 1 over cosine x. So I actually got 4, right? Is that right? Oh, we've got cosine x. I'm sorry, cosecant x. Sorry. Cosecant x. So you can take only one is given, but many are really implied by this one identity. And that's true of also, especially of this sine squared plus cosine squared. I can bring the cosine squared to the other side, and sine squared equals 1 minus cosine squared, or cosine squared equals 1 minus sine squared. So we don't just use these identities as written, we can manipulate them. And in the next video, we'll actually prove an identity.